So 12-1, I realized every one I always started with the same thing. So we're going to try to switch her up here. So 12-1, instead of okay, everybody. We're going to be looking at, in chapter 12, the concept of limits. So this is what you'll be starting with in calculus. So it's kind of that transition, our kind of overlap between pre-calc and calc, understanding what the concept of a limit is. So our big essential question in this section specifically is, how can I understand the concept of limit? What does that mean? And then use that definition of a limit to estimate limits, determine whether they exist or not, and then being able to use some properties to evaluate limits. So looking at different ways that we can figure out what a limit is. So thankfully, we've laid a lot of the groundwork for this when we talked about the end behavior of a graph, looking at like horizontal asymptotes and looking what the ends of the graph do. That's a kind of a big concept towards doing that, but we're going to solidify that even more in this chapter. So in this first part, I'm definitely hitting on how can I understand the concept of a limit and what is that definition, and do they exist or not is kind of our first big part. So define a limit. So here's the limit definition in words. So we'll write it out in words first, but then we'll write it out in symbols as well so you can see what that means. It says if f of x becomes close to a number L. So L, we're talking about L is like for limit, so that's where that's coming from, that capital letter L. So if the function becomes close to a number L as x approaches a constant, a c, a number, so that is a constant, from either side, then the limit of f of x as x approaches c, that constant, is L. So that means as I get closer and closer to a particular x value, the y value is getting closer and closer to a particular number. Kind of like when we talked about that horizontal asymptote, looks like the end of the graph is getting closer and closer to like 7. That means that limit would be 7. So sometimes it's easier to write it symbolically. So we're going to use our symbols that we know. So the function is approaching. So remember, a little arrow approaches a limit, a number, this limit L, as the x value gets closer and closer to whatever that c number is. So as like x gets close to 7, the function's getting close to 12, whatever it might be. So symbolically, this is how we would say that sentence. F of x approaches L as x approaches c. Now, the actual limit shortcut, like how you actually write a limit, we abbreviate limit LIM. So you'll see LIM. Underneath, you'll have your x approaches c. So you're telling everyone, okay, we're checking to see what the limit is as x gets closer to this number of the function, so of f of x, is equal to. So when you're answering the question, then you're saying what the limit is equal to L. So I would read that as f of x, the limit, so if this is how I would say it out loud, so for the second one here, the limit as x approaches c, so x approaches c, of f of x, the function, right, is equals L. So if I'm actually going to read it out loud, like if I wanted to read this to someone, the limit as x approaches c of f of x is L. Another way to say that is f of x approaches, this is the top one here, so approaches L as x approaches c. So that's kind of our verbiage, how we're going to be saying this. So what we're looking for is the value that it approaches. So we're going to start with a very sort of hands-on way to kind of get the gut feel of a limit. And then we're going to talk about what does it look like algebraically? What does it look like numerically? What does it look like graphically to try to pull all these together? So we're going to look at what kinds of rules there are. So we're going to start with, again, kind of the long way of doing this. It says use a table to estimate the numerical, the limit numerically, so using numbers, a table, for this function. So let's see if we can read what this says. So this is asking us the limit as x approaches 3. So I'm going to actually write it out so we know what we're saying. So as x approaches 3 of this 3 minus 2x. That's your rule or your function. So what is that approaching? So what we're going to try to figure out is as we get closer and closer to 3, what does 3 minus 2x do? So we're going to do a table. And we're actually going to do this on our graphing calculator a little bit too, so we can help see this. So we're going to make up a table. We're going to look at the x values and the f of x values. And what we're trying to find is what it's getting closer and closer to. Actually, I guess I can put it inside here. I didn't have to write it out front. We're not going to do that many values. We're trying to see what it does as it gets closer and closer to 3. So I'm going to do numbers on either side. So I'm going to do like 2.999, 3.001, 3.01, and 2.001. So we're going to do like 100th away, 1,000th away, like what's happening as it gets closer and closer. So here's what we're going to do. We're going to use our table and our graphing calculator to help us. So I'm going to go ahead and have you put in y equals 3 minus 2x. Now I want you to think about what kind of rule that is. 3 minus 2x is a line, right? So having a y-intercept of 3 is slope of -2. I'm going to go into my table. Right now it could be anywhere, right? So I have my table going up by ones. I'm going to go ahead and set my table set, so second window, to the independent variable to ask. I want to be asking specific numbers so I can just see what those values are. So I'm going to go back into my table and then we can see what those numbers are. Now, if we were in class together, we'd all be kind of dividing and conquering here, but I'm going to go ahead and put in the numbers that that I have set up here. 0.001 and 3.01. So numerically, let's see what's happening here. So if you look at the values in the table, I'm going to go ahead and transfer them over here. So we've got -2.98, then we've got -2.998, we've got over here -3.02, -3.002. I think I went the wrong way on that one. There we go. And the question mark here, oops, oh my goodness. The question mark is what's in the middle. So what is this getting closer and closer to? Now this seems like an inordinate amount of work that we would never usually do, but we're trying to get the concept or the idea of what a limit is. So as I get closer and closer to this 3 value, so as I'm going in this direction and this direction, so I'm looking at the x values getting closer and closer to 3, my idea is what are the y values approaching? What is this limit that we're looking for? So the c value is the 3. The limit is the number that we're filling into this box. So as it gets closer and closer, not only does it approach, it sure looks like it's going to actually equal -3. So if we look on either side, so I would say that the limit of this function 3 minus 2x as x approaches 3 is -3. So we're looking at what value that gets. So if we close in on either side, this is a continuous function. Not only does it approach that -3, it actually equals it. So if you go back to your graphing calculator, we're going to go ahead and graph this. So I'm going to graph that linear equation. And if I use trace, this is a great way to be able to see what's happening here. So I'm going to go ahead and turn my plots off here as well. Don't want to, oopsie, not on. I want to turn my plots off. So number 4, just so we don't have anything else going on here. When I look at my graph and I trace, what happens is I get closer and closer to an x value of 3 from either side. So as I keep getting closer and closer to 3, my value looks like it's getting closer and closer to -3. That's the whole idea of what a limit is. It's approaching from both sides. So as I get closer on each side, it's getting closer and closer to that value. So not only does it approach it, it equals it because this is a continuous graph. All right, let's take a look at another one. So I want to kind of compare and contrast here 2 different kinds of functions, and then we'll see if we can put this together and look for some shortcuts. So it says, what's the limit as x approaches -2 of this function? Now, this is a rational equation. It has a fraction. If you try to find the domain of this function, remember what you can't ever divide by, 0, right? So the domain with this would be all reals except x can't be. What would make the bottom 0? -2. So I've got a problem here. This -2 is what they want me to see what the limit is as it's approaching, and that's not even a place that's defined on the graph. So we're going to take a look and see what happens as it gets closer and closer to -2. That's our c value. So as we close in from either side of the x values towards this -2, we want to be checking to see what do the y values do. They should hopefully be closing in on something as well, which is going to be our limit, and that's the number that we're going to be looking for. So we want to see what that number would be equal to. So we're going to do numbers again on either side of this -2. So we're going to do the same thing we did last time. We're going to do, 1.99 would be on this side. We're going to do 1/1000th away and then 1/100th away. So we can get some values that we can compare. And we'll do that on the other side as well. We'll do 1/1000th away and 1/100th away and see if we can see what's happening as we close in. So let's go ahead and use our graphing calculator as a tool here again. So I'm going to go ahead and clear this. Let's put in this equation. So we're going to do an x squared plus 4x plus 4, and then we're going to divide that by the x plus 2. If you're using the fraction function, you don't need parentheses, but if you're not using the fraction function, please make sure you double check. Let's go ahead and see what the graph looks like. So it looks linear. If you remember what we were doing before earlier in the year, we could actually factor this numerator, and this is one of those removable discontinuities. Remember, we're going to be talking about discontinuity again. When I can remove it, this one actually has a hole. So it's a point or a hole, a discontinuity at that location. So it's a point or a hole on the graph. So point discontinuity, we talked about those different ways. So it actually ends up looking like the line x plus 2, but we know that there's going to be definitely an error at that x equals 2. There's a hole. If we zoomed in, we'd be able to see that little break in the graph. So if I went on either side of that 2. Let's go ahead and go into your table. We're going to try to see what's happening on this one. So I'm going to do what we were doing before. I'm going to clear, let's see, delete out these so I can have a little bit easier way to see this. So I'm going to delete out the ones that are in there, and I'm going to put in my new ones. So I'm going to do negative 2.01 and on through the list. And as you can see from the table, we get a really good read on what's happening for these different values. So we have negative 0.01, negative 0.001. Looks like it's getting closer and closer to 0 from that side. We have 0.001 and we have 0.1. But look what it's saying at negative 2. It's saying error, which it should, right? We know that the value of the function doesn't exist at negative 2. But can the limit exist? Well, it sure looks like the numbers for y are getting closer and closer to 0 on either side. And yeah, the limit actually exists, even if the value of the function doesn't. So this limit would be equal to 0. So that's a big kind of concept or idea. The value can approach, but it doesn't have to actually be continuous there to have a limit. So if I trace on my graph and I look until I get closer and closer either direction to negative 2, sure looks like the y's are getting closer and closer to 0. Looks like it's crossing there. And then if I come from the other side back, yeah, it looks like it's getting closer and closer to 0, even though I know there's a hole on the graph there at negative 2. If I zoom in on that, so I'm just going to go an x value of like negative 3, and then up to negative 1, just so you can see what's happening there. See, there's that little break right at negative 2 on 0. So it's definitely a hole, but the limit can exist, right? It's approaching the same number from both sides. So this is what you would call a numerical approach to evaluate a limit. It's pretty time consuming. Most people can see what's happening just by looking at the graph. So graphically is a really nice way to do it too. We'll talk about algebraically even easier. You don't even have to graph anything. But the idea of a limit is as we get closer and closer to a constant value, in this case it was a negative 2, from both sides, the value of the function got closer and closer to a numerical value, which was a 0 in this case. Even though the function didn't exist, the limit still did. All right, so this is the really, really big important idea here then for looking at limits. So the existence or non-existence of the value of the function at x equals c, so whether or not c is in the domain of your function or not, has absolutely no bearing on the existence of the limit. The limit can exist even if the value of the function doesn't. So if it approaches the same value from both sides, it's still going to have a limit. And that's a big part of what we're going to be talking about moving forward, being able to tell whether it's existing or not what the value of the limit is. So we're going to take a look at a lot of different scenarios when limits exist and when they don't, so you can get comfortable, or when the values of the function exist and when they don't, and finding out the value of the limit. All right, so let's take a look at some examples here. So we're going to try to estimate this limit without having to do an entire table. So we're going to see if we can go back and see if we can find the value of the limit without having to make the whole table or do it numerically. So let's talk about domain here first of all. So this is a rational function again. If I set that denominator equal to 0, I could use everything except for the value of 2, right? If I set the denominator equal to 0, 2 is going to be a problem. So they're asking me to find the limit as x approaches 2. So I know I can't evaluate this function at 2. I'm not going to be able just to plug that number in. So what we're going to try to do is see if we can evaluate this function in a little bit different way. So let's take a look and see if we can graph this. So can you go ahead and get this into your graphing calculator? All right, so when we take a look at that equation on our graphing calculator, it ends up looking like a parabola. So let's use the graphing approach. We could use the table too, but let's look at the graphing approach and see what happens. I'm going to go ahead and hit trace. As x gets closer and closer to 2, see if you can guess what the y value looks like it's getting closer to. So as x gets closer to 2, so we're doing a graphing approach now. What does it look like the y value is getting pretty close to? If you had to guess, if it was a whole number answer, what do you think that looks like it's approaching? Kind of looks like 7, doesn't it, if we look at both ways there? So we know that there's going to be a hole. I'm going to go back to my table set here, and I'm going to go back down to auto and just take a look at my table. I know at 2 it's saying error, and it should, but I can look and see what's happening as we get closer and closer by looking at the graph, and gosh, I think it looks like it's getting close to 7. Is there a way that we could see that algebraically? My guess here is a 7. Let's see if we can do that. And remember in the last one, we could simplify that expression. So that definitely didn't look like a cubic, right? It looked like a parabola, a 3/1. It must mean we have a point discontinuity, a hole. So this is a hole in the graph, right? A point discontinuity. So we must be able to simplify this expression. So all that stuff that we did earlier in the year with simplifying is going to come into play again. So if you see 4 terms, how do we factor that? 4 terms is factoring by grouping. So let's see if we can factor this and see if we can come up with a simplified version. I can pull an x squared out of the first 2, so x minus 2. I can pull a 3 out of the second 2 terms, so x minus 2. And if we factor by grouping then, that's going to leave me with x minus 2 times an x squared plus 3 over an x minus 2. And then I can reduce that fraction. What that's going to allow me to do then, the limit as x approaches 2 of x squared plus 3, that really looks a lot like the graph that we have now, right? So if you think about this picture, up 3, that's where your vertex is. Again, we have a hole right at 2, but how can we get the 7 from this? So we guesstimated what the 7 from looking at the graph. Can you see how we could get a 7 as we're looking at x approaches 2 from this expression? What if we just plugged in the 2 now that we can and evaluated that? Wouldn't that give you the 7? And that's going to be our direct substitution that we're going to be able to deal with. So kind of the shortcut algebraic approach that we're moving towards here is being able to look at just the sentence without having to do the graph and trace. I can actually just simplify and be able to solve. So we're going to be looking for that and be able to calculate what those values are. For right now, again, we're looking at numerically and graphically, but we're going to be able to do the algebra as well. If you go back to the previous one that we did, remember we simplified that down to the limit as x approaches -2 of x plus 2. Guess what? Once again, if I plugged in that number now, -2, because I can now, I would get that 0 for that limit. So being able to directly substitute is something we're going to spend a lot of time on. Let's go back to the very first one we did. Remember, we got the -3 by looking at what the values got closer to, but what if I just substituted in the value I was trying to do? So 3 minus 2 times 3, that would be 3 minus 6, or -3, that same exact limit that I got. The reason I could just substitute directly right away is this was a continuous function. I didn't have to worry about those breaks in the graph, the hole. So continuous functions, the value exists, and so we can find that limit a little bit easier algebraically. For both of the other examples we talked about, it was discontinuous at the place we were trying to find the limit. So for both of those examples, if we want to do it algebraically, we had to do some factoring and reducing first to be able to do that. Or you could do the tables like we did numerically, or you can look at the graph. We have lots of options in terms of solving and being able to do that. All right, so let's talk about what happens if it doesn't. So take a moment. We're going to watch it. So we're going to talk about, if you've ever seen Mean Girls, you've seen that. The limit sometimes doesn't exist. There's ways that limits don't exist. So we want to take a look at what those options are and show an example of each one so you have an idea. What would make a limit not exist? The 3 examples we talked about already today did exist, but when doesn't it exist? All right, so here's the first one, and I had to kind of make it a little bit bigger so we could actually read. So if you'd want to just follow my 1, 2, 3 here. So first kind of way that it doesn't exist is if the function value approaches a different number from the right side than it does from the left side as you get closer and closer to C. This one's called a jump discontinuity. We saw those like in the greatest integer function, like the step function, things where it doesn't have the same value on one side as it does from the other, or those piecewise graphs we did earlier in the year, like like say you have one part of the graph goes to there, the next one starts from there, it's jumping between those two values. So if it doesn't approach the same number from the left and the right, it's not going to have a limit at that particular value. So at this particular x value, at that c, it's not going to have a limit. It could have limits in other places along the graph, but not at that location where it jumps. So in these places where it jumps up to the different step would not have a limit. The second way you don't have a limit is if it increases or decreases without bound. In other words, if you have like a vertical asymptote going on. So if you're looking at an infinite discontinuity, we would call that. So an infinite discontinuity, that means you have a vertical asymptote, something that's growing without bound or getting smaller without bound. That's going to be a place where your graph is going to be discontinuous. So if you have something where you have a vertical asymptote and on one side your graph is doing something like this and on the other side it's doing something like that, you're at this location where these are getting huge or getting small, you're not going to have a limit. It's going to either be infinite or negative infinity. So it's not approaching a value. So it gets bigger and bigger and bigger. So if it increases without bound as you get closer to C, in other words, you have a vertical asymptote, no limit at that location. Again, it can have a limit in other places. And then the third way you cannot have a limit is if something oscillates between two fixed values as it gets closer and closer to C. So oscillation, like if you think of something swinging or something like that, it's going back and forth, back and forth, back and forth, back and forth, and it's never settling down on a single value. You see that with like sine and cosine kind of graphs. It's never going to have a limit either. So it's going to keep going back and forth. So we want to take a look at one quick example of each one of those scenarios so we can talk about them. All right, so let's do one of each here. So let's take a look and show that the limit does not exist. So we're going to take a look at the first one. It's going to be super helpful to see what the picture of this looks like, and we're going to talk about domain. So let's talk about the domain first of all. So set that bottom equal to 0. The domain would be all reals. X is not going to be able to be equal to 1. So where they're asking us to do this limit as x approaches 1, we're not going to be able to have a value there. But the idea is what's happening as it approaches from each side. So let's go ahead and see if we can graph this one. All right, so go ahead and get that typed in there. Be careful that you have numerator and denominator. And let's take a look at the graph that you get. So we have two definite horizontal segments here. So we have one down at -2, we have one up at +2, and the oopsies, the location that we're talking about here is right at 1. So we're looking at that place at 1. So I'm going to go ahead and make kind of a replica here. All right, so as x is getting closer and closer to 1, so we're talking about going this direction and this direction. We're looking closer and closer to this c value at 1. Is it going to have a limit? Well, here's our issue. F of x, the value of the function here, is approaching, down here, all these values are at -2. As x approaches this -1, and we're going to say from the left, because this is the left-hand side of the graph. So to say from the left, we're going to put a little minus sign, and we'll talk lots more about this, but left-hand and right side limits. So as you come from the left-hand side, the easiest way to say that mathematically is just to put a minus. It's approaching -2. Let's look at the right-hand side limit. As I get closer and closer to this one from the, oh, not -1, +1, I'm sorry. The c value that we're looking at is +1. So as x approaches +1 from the left, it's going to -2. But the function up here, f of x, is getting closer and closer to +2 as x approaches 1 from the right. And guess how we say from the right with the positive? They're two different numbers. One's going towards -2, one's at +2. In other words, it jumps right here, right? There's a jump up to a new value. So at x equals 1, this is a jump discontinuity. So that means the limit would not exist, right? This is going to be a place where it is discontinuous. So this is one of those where it approaches a different number from one side than it does from the other. So the limit does not exist. So what you'd be showing to prove that is these two different sentences. So you'd be showing that it approaches a different number from one side as it does from the other. So that each side is different. All right, let's take a look at the other two ways. So why doesn't this limit exist? All right, so first thing I want you to do is go ahead and graph it. All right, so our equation, -1 over x squared, this is kind of the volcano graph or the funnel graph. Take a look at what's happening as x approaches 0. So I'm going to go ahead and kind of replicate this so I can draw on it. We're looking at what happens to the value of the function as it gets closer and closer to 0. So I'm going to make a little picture of this so we can talk about. All right, so on this graph, as x is getting closer and closer to 0, so we're looking at each side getting closer and closer to this c value of 0, what's happening on the graph? Well, this one's going infinitely small from the left, it's going infinitely small from the right. In other words, there is a vertical asymptote happening on this graph at x equals 0. If you do the domain of this function, set that denominator equal to 0, x can't be 0, right? We can't divide by 0. This isn't, though, a jump discontinuity like the last one, and it wasn't a point discontinuity. We can't divide out the x. There's no way to simplify it. This is an infinite discontinuity. We can't get rid of this. So this is a number that we can't deal with. So it's an infinite discontinuity, which means there's a vertical asymptote at x equals 0. So that means the limit does not exist. So the limit can't exist. So the limit, and we're going to use d NE for does not exist. So the limit does not exist at x equals 0 because there's a vertical asymptote. So the limit does not exist. So that's our kind of abbreviation for it. So does not exist at x equals 0 because there's a vertical asymptote. It's getting infinitely small on both sides. We can't have a limit there either. So in the last one, the limit didn't exist because it jumped. This one, it was infinite. Let's take a look at one of the oscillating ones. So if you can go ahead and type in your limit of sine of 1 over x, make sure you're in radians. We get a really interesting looking graph. So what you get is this oscillating thing going back and forth. So when you see it on your graphing calculator, it'll be the same thing. So on your graphing calculator, you might see something more like what I have here. If you zoom in, like what is up on my screen, I went from -1 to 1 just to kind of see what's happening on either side of 0. You can see that getting much more kind of compressed going back and forth. This is that oscillating one. So it's going back and forth between 1 and -1 very rapidly. So this one, the limit is not going to exist either because it's oscillating. So the idea behind it is showing that you're going back and forth between different numbers very rapidly, and you would not have a limit. So this one is oscillating as x approaches 0, so the limit does not exist. So our approach today is really been kind of talking about 3 different ways to look at limits. We can look at tables, which I could do a table for this as well, so you can see what's happening at either side. So we could do this kind of more what they would consider numerical approach. So you can look at a table and do numbers on either side and see, hey, what is happening as we get closer and closer? It's going back and forth. That's why this one doesn't. So we can numerically approach. We can look at a graph. So we can take a look at a graph and trace on a graph. This would be a graphing approach to see what's happening as it gets closer and closer to a value. Ultimately, though, heading towards the numerical approach, being able to substitute values in like we started to do on some of the ones earlier, is great. Now remember, though, there's 3 different ways you cannot have a limit. So if it's oscillating, if it jumps, or if there's a vertical asymptote infinite. For the other ones, we're hopefully going to be able to reduce out those point discontinuities. So even if it's not continuous, we can still evaluate the limit. If it's continuous, we can always evaluate the limit, and we're going to be looking at all sorts of different strategies to be able to do that over the next couple of sections.